Hello, my name is Ashley Goodnight, and this is my Lab 5 report for Physics 2212. Let's get into our introduction. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube, use GlowScript to model the data, and compare these theoretical and observational values. We care about this experiment because it allows us to practice key physics concepts, including Faraday's law, and to gain familiarity with the GlowScript modeling software. In the end, I successfully used Faraday's law and Newton's second and third laws of motion to create GlowScript code that modeled the motion of the falling magnet through the aluminum foil tube. Here are the measurements I took during the experimental phase of dropping the magnet through the foil tube. All of these values were inputted into my code, which we will now take a closer look at. As stated previously, I first inserted my measurements to code the geometry of the tube. For the second part, I inputted the mass of the magnet and my mu value from Lab 3 earlier in the semester. Now onto calculating the magnetic field. I also pulled this code from our third lab. As for calculating the magnetic flux, this equation came straight from the EDX videos. Moving on to calculating the net force and updating both the position and velocity, I simply applied Newton's laws of motion. Finally, let's look at what all of this code produced. Here is what my GlowScript produced. You can see the magnet slowly fall through the foil tube and the corresponding plot of velocity versus time. We were then asked to answer questions in order to interpret the simulation. The first question asks, what happens to the dynamics of the system when you flip the magnet around? Well, when you flip the magnet around, the sign of the magnetic dipole changes, so I made the necessary changes to my code. As you can see, the color in the GlowScript model changes, which indicates a change from the field being clockwise into counterclockwise. However, notably, the time it took for the magnet to fall is the same for both. The next simulation question asks, how does the total in-time tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? Actually, my observational and theoretical time were really close, and I have the valid excuse of my poor reaction time to account for the difference. During the experimental phase, I started and stopped the timer on my own, which carries some inherent error in the timing. Let's get on to the next question. This part asks, what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? Here is the plot for my GlowScript code. As you can see, there is a long period of time where the velocity is constant. So we know, thanks to Newton's second law, that the forces acting on the bar magnet sum to 0 for most of the fall. Finally, we can move on to the conclusion questions. Let's address the first conclusion question. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? As I decreased the resistivity of the conductor in my GlowScript code, the time for the magnet to fall through the tube conversely increased. So I think that if I were to decrease the resistivity as close to 0 as possible, the magnet would float, never falling. Now on to the second question. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? Well, introducing holes or slots at areas with decreased current. In the absence of aluminum foil in different places along the tube, there will be places where the magnet will fall faster. Instead of the flat line in the center of the velocity versus time graph, the slope would fluctuate up and down. Thank you for watching. If you would like to see my GlowScript code in action yourself, the link is in the description of the video.